Good morning, Tom. I'm Patrick. I'll introduce the slides in group two here. Do you guys want to do introduction or just wait?
Yeah.
Okay. So I'm Patrick. This is Sophia. She'll stand.
Right here.
And then you guys.
Sophia.
Or-
Hi, I'm Gabe.
Hi, I'm TJ.
I'm Colton.
Hello, I'm Alex.
Justin.
Hi, my name's Michael.
Hi, and I'm Samuel.
So this is our group two, again, AG1, Attack Gator 1, and this will be the final presentation of our overview and our test flight. Your arrows weren't working there. Not touchscreen, sorry. Okay, so concept and criteria of Attack Gator 1. We wanted to re-simulate like an A-10 Warthog, so that's what we were basing our plane off of in our design, because the A-10 Warthog is supposed to retire at the end of the decade for the United States Air Force. So the goal is to create a more 6th-gen type close air support fighter to stay ahead of our global adversaries. So we have the first prototype from the remote control model that had a crash, but we are in a design of a prototype B, which we will show near the end of the slides. So initial trial, of course, would be the 3 laps around the Flying Gators test course in under 5 minutes. We estimated a cruise speed of around 80 miles per hour with our 2 64mm EDFs or electronic ducted fans. And AG1 also must be stable for weapons, platforms, and maneuverability for the high speed, high maneuverability flights.
Okay, looking at the overall dimensions and specs that we designed this plane to have, it will have a wingspan of just under 5 feet and an overall length of a little over 6. Are you gonna click through?
Yeah.
Okay, yeah, so you can take a look at the other specs. We'll go through the different views of the CAD model of the plane also. So this is our idealized version of what this aircraft will look like. Looking at the top view, there's a few different measurements here, the 24 inches of the nose, the whole fuselage being a little over 6 feet. And then the wingspan of a little under 5 feet, and we have a tail with a wingspan of 24.8 inches. Okay, the side view here, we designed it with the center of gravity is just in front of the aerodynamic center, so it should be stable. We'll look at stability more later in this presentation, and the batteries will be sitting out here really close to the nose. And then in the front view, we see that the largest diameter of the fuselage will be 7 inches.
We constructed the model completely out of PLA plastic using super glue and JB Weld adhesive to bond them together. We utilized 3 3mm carbon stringers in the fuselage and 2 aluminum tubes as wing spars. And then we also used 9-gram and 17-gram servos for all the control surfaces, except for the horizontal stabilator, which we replaced with a 45-gram Traxxas servo. We also used 2 LiPo batteries to meet peak power requirements.
We designed our wing with the goals of the plane in mind. We went with a high shouldered wing for its stability effects that we would see. We also went with a high taper to get an elliptical lift distribution over the wing. And we ended up going with a 2415 NACA airfoil for this to generate the most lift during our flight condition. Now, here is a revised version of the internal structure of the wing. Before, in our midterm presentation, we mentioned the lattice structure, but we changed to a more traditional spar and rib structure. As you can see here, this is the outer section of the wing. This is the outer section as it came out from the print. We have our T-joint for landing gear, where the aluminum spar runs through all 3 sections. We have 3 different rib sections here, and we had lightning holes put through all of these extra spars and as well as the ribs. Now, we also redid our structural calculations based on what Mr. Singer had given us the idea to do before. So what we did was I used the same formula from the same paper to do the moment at the root. And I used a percentage to calculate what load was gonna be on the front and back spar. And I used the distance from the aerodynamic center of the entire wing to define that. And when we actually ran through these calculations, unlike before getting 1,000 factor of safety, we ended up getting a 1.8 factor of safety at 7 Gs on the front spar and around a 2-ish factor of safety at 7 Gs on the back spar. So much more ideal for what we're looking for here. And you can see here, go back. You can see here some of the actual structure. You can see the aluminum spars running through, going through these thrust tube sections, kind of supporting where all of our thrust is moving through, moving that into the fuselage. And in the back, you can see the longer spar that runs through those outer sections of the wing, as well as some of the stringers that we have.
As we do have a heavier airplane, flaps were necessary to meet the runway, the takeoff distance requirements. And they were designed for a 25% wing area specification. And here you can see the actual flaps, which were able to deflect to both 20 and 30 degrees.
So we also, from the midterm, we took also some feedback and redesigned our horizontal stabilator just a bit. So again, yeah, we, instead of doing a normal elevator, or split elevator, we did a split movement horizontal stabilator to create more moment and more lift on the tail section as well for higher maneuverability purposes. So as you can see here, this highlighted in blue, that was our servo mount that we had that we attached inside of the tail section of the fuselage, just on the opposite end of this bulkhead, which that included a 2075 X-Traxxas metal gear servo with 125 ounce-inch torque value, which is a big enough torque value to create that movement that we need instead of like a 17-gram metal servo that we were originally going to use, which could have very well snapped the arm because of the high force that we have on the stabilator. Next, we have the spacer here, which you can see in between the shoulder of the fixed shoulder of the fuselage and the movement of the horizontal stabilator. And that's just that eliminates any friction that we could have here. So inside we have a bearing and then the spacer as well to create more movement and less friction. In addition here, we have running from this end to this end because it is symmetric. So I just took the left view and section view here. We have a 4mm by 6mm by 420mm in length carbon fiber tube, which runs the length to the outer section of each horizontal stabilator through the fuselage. And that's also used as our torsion rod as well. So it gives us more support in our tail section for our flight control surfaces, in addition to the torsion rod assembly, which we have. And here, the 3 holes on the bulkhead, those are also used as 3mm carbon fiber stringer holes as well. In order to, this bulkhead will be not only super glued to the other aft section fuselage areas, but in addition, it creates that shear joint too, just in case super glue may become undone. We have our shear joints there as well. Slide. So this is more of a upper section view, so top section view just at an angle. The vertical stabilizer, that'll be on the next slide, talked about by Gabe. But as you can see here, more visualization of our stringer holes. We have ribs and more spars running through. The carbon fiber spar runs through there. And then spacer, and then again, it's symmetric on that end as well. And then just a better view of the servo mount we have that'll be screwed in. Servo will be screwed into here, and the servo mount's super glued to the bulkhead and the other fuselage ribs we have inside the aft fuselage. And then here again, here's a torsion rod attachment. So from the midterm, we had a split torsion rod that was glued into the shoulder joint we have. We made modifications to where now this carbon fiber spar will just run straight through and it's a uniform spar now instead of having 2 spars glued into one. So it's a little bit more structurally sound. And this shoulder joint will also be attached to this servo push rod arm linkage. And that's how we connect our servo with the push rod to the torsion rod in order to make everything move. So that's our mechanical linkage factor there as far as the whole horizontal stabilator as one. And again, just to sum up the things I've talked about. So horizontal stabilator, reasons why we did it was because of higher maneuverability, resembles more modern day agile aircraft. quicker climb and descent, quicker turning to avoid any enemy missiles fired, just a simulation of, if this plane was in real life. And again, that would create that bigger CM alpha, so bigger pitch moment that we would want. And then again, the fourth rod assembly reasons why we did that was because of, it was more efficient for the limited space we have back there in the tail section, lessens the amount of servos we would need and also the wiring, and ultimately reduce that weight and easier manufacturability, that we can put everything in the fuselage as one servo with everything connected on the outside instead of having wires come through the horizontal stabulator with like an original elevator type of tail. And we also tapered everything on the horizontal stabulator, just like we did with the wing, in order to create more efficient airflow, reduce drag, increase lift for the quicker speeds we have estimated.
All right, so for the vertical stabilizer, this was just a concept when we did the midterm presentation, but we split it into 4 main sections. We have the vertical tail shoulder, we have the 2 pieces for the actual vertical tail fin, and we have the rudder. This vertical tail shoulder was actually split into 4 sections for printing that were glued together with bulkheads like this, but they were smaller on the inside. We tapered the vertical stabilizer to allow reduced drag, and we chose a conventional tail to keep the wake of the EDFs off of the stabulator. We also chose the single torsion rod assembly so that it would be more efficient, it would reduce weight, and as it says, it's inside and we designed a servo system inside of the fuselage of the aircraft to protect it from possible enemy fire with the fuselage and to make sure that it's not on the outside of the plane aesthetically. All right, the vertical tail servo design we did a 9-gram micro servo with a push rod system. The push rod went from the servo horn into this linkage piece right here. The linkage piece was glued to the vertical tail torsion rod, and that's how the torsion rod worked. The vertical tail was attached using this shelf that was designed to provide a shear joint between the tail and the vertical tail shoulders so that it was secure and wouldn't come off. These ridges actually go inside of this tail. These slits accommodate these 3 ribs in the vertical tail to slide in here, and there are 3 2-millimeter carbon spars that go down into these holes. There's also a free fit hole in the vertical tail shoulder to accommodate the torsion rod so that it can go down into there. This is the overall structure of the vertical tail as seen from a section view. The torsion rod system's here, there's glue inside of the rudder piece. And these are the 3 carbon fiber rods that run through the entire tail and hold it all together. All right, onto internal structure. Based on past feedback, we decided to get rid of all the double-walled structures. And we also added a guided stringer hole so that the force would be distributed along the fuselage. Our internal structure has bulkheads, which allow it to attach to each other using super glue, but also the stringer holes go through all of them too with these guided holes. And it has ribs and spars throughout, which gives it a little bit more rigidity, but without that double-walled structure, so it reduces the weight there. A little bit about the internal structure in the nose. The nose was made of 4 parts for printability. It was around 24 inches long, so 6 inches per piece. Here, this is where the battery is located. This is in the second part. You can see some locator holes that we had for pegs. And this wall in the center is where we mounted the batteries. So the batteries go on the 2 walls in the middle there. So for the landing gear of the nose, this is the 3rd part of our nose. Here we have where the landing gear of the nose goes. It has thin wall structures in all 4 directions to keep it from buckling in the 4 directions. The servo is mounted on this wall over here. So we have 2 thin wall structures, which not only provides support from bending, but also provides a mounting surface for the servo to turn that nose
We also have lightning holes throughout those walls to keep it a little bit lighter. And here is where the stringer goes through. The stringer goes all the way up to where the landing gear goes, which provides a little bit more of that load carrying capability. Other way. There we go. And here's a picture, actually a video. Could you press play on the video? There we go. So this is a little bit about how it looked in real life. So here's the servo mount attached to that wall I was telling you about. And so the torque is transmitted via a push rod from the servo to, we had a 3D printed part, a custom fitted part that goes to a rod that connects to the landing gear. And so that's how it was connected there.
I go to this. So for our main landing gear, we continue to use the T-joint to mount it directly to the aluminum spar running through the wing. So this is where the T-joint would be located, and the attachment rod for the wheel runs directly and makes physical contact with the aluminum spar. So here's what that looked like in implementation. So within the T-joint, we reinforced the rod of the landing gear with JB Weld. So at this joint, the rod was JB welded in, and where the T-joint met the wing itself, it was also JB welded to prevent vibrations during the taxi test. And due to our our high wing, the landing gear needed to have an extension. So we used an aluminum rod for that, as you can see here, but there's a little bit of deflection. So we decided to put a carbon fiber sleeve around that aluminum rod to kind of mitigate that. And this was all connected with set screws to that rod, where the aluminum rod was dremelled out kind of like a motor shaft to where it was a D, so the set screw would sit flush. Next slide, please. So then for our propulsion system, we kept two 64mm EDFs, and our ideal thrust to weight ratio based on our initial weight estimate was 0.47. This was at a 75% throttle for our cruising speed, and that would generate a maximum thrust of 2.14 kilograms.
So when you're using an EDF for propulsion, it's necessary to have a thing called a thrust tube. Basically, what that does is it just makes sure that flow is regular through the fan and it comes out regular. Another thing with using the high wing and the sort of armpit configuration that we're using in this plane, it's necessary that we have something routing it through instead of getting that dirty air that's in the fuselage, coming off of the fuselage and under the wing. So the duct system was optimized for these flight conditions, for the flight speeds we'd like, and we'll see in the next slide a CFD analysis. It's about 68 meters per second coming out of the back end, so that's exactly what we'd like to be for our thrust flight conditions. And right here, you can also look, and we have a boundary layer diversion ramp that gets that dirty air away from the EDF. So we're sucking in nice clean air and getting the most out of our thrust system.
We performed a heat transfer analysis because we figured that we're drawing so much power from the EDFs. We might have a thermal failure mode. So we focused on the electronic speed controllers because they have the most current and voltage running through them. So the current from the ESC is at cruise is 37 amps, and the voltage from the batteries is 14.8 volts, which gives us a power of 67.6 watts. So that's the energy flowing into the electronic speed controller. So in order to that energy has to exit the electronic speed controller somehow, or else it's going to fail. And so the mode that it exits is via convection to the outside, and it's going to convect outside of the fuselage. So at cruise, we have a convection coefficient of air at, it's about 34.6 watts per meter squared Kelvin. And the convection area is about 0.036 meters squared, which gives us a thermal equilibrium where this is where the heat transfers are equivalent. Heat energy flow in equals energy flow out. So we achieve this thermal equilibrium about 54 degrees Celsius above atmospheric temperature. So atmospheric temperature is about 30 degrees Celsius. So this gives us a final temperature around 90 degrees Celsius, which is below the melting point of PLA, which is perfect for what we're doing. Moving on to the design stability. So we targeted a 7% static margin with a CG about 0.94 inches in front of the AC. And we could adjust the CG by moving the batteries forward and backward in the nose if we so desired. Right here, we used XFlyer for all of our stability calculations, and this is an example of the center of gravity calculation from XFlyer. We performed a static stability analysis. So we obtained the roll, pitch, and yaw moment derivatives with respect to angle of attack and side slip. So the roll and pitch moment derivatives are negative and the yaw moment derivative is positive, which means that upon encountering an atmospheric disturbance, our aircraft is going to return to trim condition on its own, which is good. Right here we have a graph of our CM alpha. So this here is the slope of that graph, and that's how we obtain all these. That's how we obtain all these values. And then down here we have a diagram of the lift distribution from the wing and the horizontal tail. We also performed a dynamic stability analysis on our aircraft. So dynamic stability is split into two major components. You have longitudinal dynamic stability, which deals with pitch, and then lateral directional, which deals with roll and yaw. I'm focusing on longitudinal dynamic stability. Sophia will show the lateral directional. For longitudinal dynamic stability, it's dominated by two modes. We have the phugoid mode and the short period mode. So the phugoid mode is characterized by these long and slow oscillations in pitch. And the short period mode is characterized by these short and more quick oscillations in pitch. And so both of these modes for our aircraft are stable because the eigenvalues obtained from our stability analysis have a negative real part, which is good. So we also have two diagrams. So right here, the short period mode, which I'm going to play for you right now, just to show you what the modes kind of look like. And then the phugoid mode. So you can see the long and slow oscillations in the phugoid mode that I was describing earlier. And then the lateral directional stability, Sophia will, oh, they're not done. Sorry. I have some technical difficulties with these videos. There we go.
Okay, so for the lateral directional stability, looking at the eigenvalues, we see that the negative real parts of the roll and the Dutch roll modes symbolize the fact that they're stable. We'll look at some more animations on the next slide, but also the imaginary part of the Dutch roll mode will show oscillations before it fully stabilizes, but the negative sign of the real part is a good sign for stability. And then the spiral mode did have a positive real part of an eigenvalue, and that is a sign of instability, but that's usually common in aircraft design because that can be adjusted by the pilot. Okay, so then we'll play the animations. Yeah, you can see that the roll mode is returning back to its stable position with no oscillations. Good sign of stability. In the Dutch roll, we'll see it oscillates a little bit, but it still returns to a stable point. And then the spiral is just gonna run away. But ideally, that would be adjusted by pilot intake. Okay, so that was all of the preliminary design, then we moved on to construction. So in terms of the structure, all components were 3D printed using PLA and Mark III and Mark IV Prusa 3D printers that were provided in the lab. So here's an example of one of the bulkheads printing. We did use structure material. That's what these little circles are. They come out like little trees. And then yeah, so all of these components were then mostly they were glued together. Some of them, like the EDF duct cover and some parts of the nose were actually fastened in with some screws. But other than that, everything was held together by glue. And then the stringers and aluminum rods that went across through the wing box and through into the wings were just slid in through some holes that were 3D printed into the main parts of the plane.
All the electrical components were wired into the 6-channel receiver, which was in the wing box area of the plane. And we used Y splitters and reverse servos to make sure that the transmitter properly actuated the control surfaces. And here you have a picture of the wiring that was more organized after we finished and tucked into the wing box area. And this is a zoomed in picture of the wing aileron servo, where you can see our 3mm steel rod attachment, as opposed to a bent push rod that had wiggle and slop to it. We decided to use threaded fasteners for all the control surfaces except for the rudder, which required less torque on it.
Yeah, so the final assembly, this is the AG1 complete as a final assembly here. I think this should be a video. Okay, sorry, maybe that's another slide, but here they can see the whole nose section is landing gear, the main landing gears, the EDFs, the ailerons are in red, flaps are in green, and the rudders in orange, and then horizontal stabilators in black. So that's the fully completed model that was duct tape glued and had the stringers and everything involved. This is just a taxi test we did the night before the first test flight. You can see you'll see the ailerons deflect, flaps deflect. You see the rudder move, horizontal stabilator move, and the nose landing gear will also move according with the response of the pilot input, which was Mike. As you can see here, we have the steering nose landing, which means it's steered as Mike use the rudder input, because the rudder, if Mike wanted to turn right, rudder would deflect right, nose wheel would move right, and that's how we create that right turn. It's also that's necessary because of when we're landing, especially taking off too. If you don't have any nose wheel input, it could run off the runway and crash because of any torque moment or force provided from the EDFs. Next slide.
So having done all of this, we were ready to test fly the airplane after doing a few taxi tests on the Flying Gators RC aircraft field runway. We deemed it ready to fly, and we'll take it away from there. So we, throttle up 100%. We start moving down the runway. I commanded that input to get it off of the runway before it ran off. And you're now looking at the airplane going to stall because of weight issues that we will be discussing later. But as you can see, it ran off into the bushes, crashed, unfortunately. But our failure analysis will show why that happened.
So overall, the plane was simply too heavy for the initial thrust that we had designed. If you take a look here, you can see that our Initial estimated thrust of weight at that 7 pounds range that we began with is around 0.6, it was 0.59. And what ended up happening was the plane, with all the changes that we made during the manufacturing process, ended up weighing like a staggering 13 pounds, which was significantly heavier than the initial estimate that we had created, which caused a lot of the problems that you see in that flight. You could see that there was a lot of control problems. He was having to bring it into a stall even to climb at all to get enough lift out of the wing. And the thrust just wasn't there to actually get into that climb. And overall, that just made it, one, impossible to turn, and two, extremely hard to keep in the air. And so that's why you see the failure that happened. We checked the CG before our flight and everything looks good. We had several people to confirm and check what we were doing and make sure that those things were good. It was very structurally sound. You'll see a picture of the crash in a minute, where we only lost one wing during the crash. There was also some issue with warping of the PLA due to color. You can actually see in the crash picture that the red and green aileron and flaps had no warping at all, but all of the black and dark blue surfaces experienced some pretty major warping. So we want to correct that in the future, but we'll talk more about that in a minute. Just overall, the airplane was too heavy, and that's why we're working on redesigns as fast as possible to get this thing in the air, because we want to see it fly.
So you can see here, obviously the damage was not, well, it's bad, but not too bad. Most of this side was preserved. The only bad part was this bent aluminum rod here in the wing and the nose breaking off, but such happens when you crash an airplane. But obviously the structures were good. They were able to take that hit mostly. So the problem really just lies in perhaps lighter materials and maybe a resizing, and when we'll go into that in the next slide. So we have a few options. First option being, if our ESCs allow, maybe we can get a larger 5-cell battery, push more power through the EDFs and get it to spin faster and take off. Another thing is maybe we just redesign propulsion systems, use 80mm EDFs. Those two are quick fixes. However, shipping and our system of commerce, it's entirely dependent on that. The more sought out and time consuming fixes are a complete redesign, which is what's being pursued right now. We're also exploring these options as well, but we have to see what kind of time we have shipping. But as of right now, this is being pursued. We're going to basically redesign the aircraft, make it shorter, lighter, use lightweight PLA, definitely decrease the diameter of the fuselage, maximize or optimize for just holding the batteries and the EDF systems. And we're going to make some other changes like decrease fuselage length, which we can do because we're using stabilizers, more area, more force. So we can reduce that moment arm and get the same effects for regular elevators. And so put the next slide. So basically, in conclusion, while our test flight of the AG-1A model was not a success, we have learned valuable lessons. So we're going to use this as a motivation to fix it, see, examine more in what went wrong, and we're going to fly again by the end of the semester. And basically, like I said before, research is being conducted, and our elite design team, Group Z, has been tasked with the redesign of the aircraft. And you'll see that in the next slide, what they've been able to do. As you can see, our tail tail connector between the tail and the fuselage has been reduced in length. Our diameter has been reduced. It's now 5 inches, and we're considering using lightweight PLA. Preliminary assemblies in SolidWorks say it's 7.1 pounds, and that's just all PLA. So we're going to keep working on it to get that weight around 7 for our designed weight. Thank you all very much, and we appreciate your time coming here. Thank you.
Thank you, great job. Tom,
Yeah, hey, God, you guys, you blew through the weight, right? You get an extra 60% extra
Tom, are you
weight, is
there?
that right? Yes, I believe so. Maybe I'm muted. Can you hear me?
Is the volume on? So you do the whole five.
Can you hear me?
Hello?
Test 1 2, test 1 2.
We cannot hear you, Tom.
Okay, let me, how about, somebody else go real quick?
You connected the Zoom through your phone and see if the volume was higher.
is he on Zoom?
Yeah.
Oh, okay.
He said someone else go. I'll try calling back in.
He said someone else go.
Someone else asked about this, what are you saying?
Okay, I guess I can.
Give it to us, Duncan.
So, first, of course, overall, I want to talk about the presentation part and the slides. I feel this it's all weird. This 0 pages like, I feel like it's too many words on on each side. And also, you can change page 2, page 3. Purely for the presentation and PowerPoint itself, yeah, I mean, why you leave the bottom half like nothing there and you like push like all the words to upper half and I don't understand. Page 3. Why? You can make it larger. I mean, it's much easier for people to read if you make it larger. I mean, why you put so much like space with nothing and just like put so small word there and try to read. This is part I don't really understand. This happen like in certain slides.
I think the overall objective with that was just to keep everything uniform in sound, so like trying to keep all the font, like the title font's the same. In addition to the fonts here, trying to keep them all within the
No,
same
you
font.
don't want to keep it same like for every page or anything. For each page, your goal is comfortable for the audience to read. If it's too tiny, well, you have space. Why make it so tiny? Right? Make it larger. It's more comfortable for us to read. And page 9.
Hey, Ting, if you don't mind, can you guys hear me?
So, I was curious, so you have the 9 gram, 17 gram, and 45 gram servo. Do you guys have like any calculation to show me why someplace 9 gram is enough, why someplace you need 45? Is it necessary or is any calculation, any analysis for that part?
We did an X flyer calculation once we were there was no calculation up front, and when we were putting it together, we realized that the servo that was chosen was not going to be enough based on the design of it. And so we
Why is not enough?
the weight of the plastic itself was not considered in the
Okay.
initial calculation and what that would do to the stabulator.
Okay,
And that had a certain weight to itself because they were so large.
okay,
And so when we were doing that, we had to say, all right, well, like, what is our lift gonna be? What is the weight of these parts? And simply the 17 gram servo would not hold it. So we were forced to go back. We did that calculation and we realized that we needed something closer to the 45 gram, which is just barely within what would actually work for that part, but it was a last minute change
okay,
based on design failure.
okay. Show me the calculation in your final report.
Yes, ma'am.
We will. I was under the impression you didn't want calculations or equations in the presentation.
I mean, you need to persuade me, why do you need 45 grand? Right, I want to know why it's necessary. Yeah. Page 12. So your calculation is based on 7G, for RC aircraft, I feel like it's super ambitious, is it really necessary?
I mean, several RC jet aircraft at the speeds that we were anticipating get up and end up pulling more than this weight, actually, for like high maneuverability.
Yeah,
aircraft.
because the group, right, before you guys, they use 2.5, so you guys use 7, of course, I would feel like it's necessary.
Well, the group right before us had a much smaller aircraft with a lot less thrust.
Yeah.
So I don't think it's really fair to make that comparison. In terms of like the total design
There's a range
calculation.
for RC airplane.
Right, but if you look at RC jet aircraft,
Okay.
and I can find sources for you as
Yeah,
well. and
as
put it in the
long as you can
report.
put it clearly in the final report, otherwise you just put 7G there, I feel like it's really necessary.
Dr. Ting, if I may, the trainer aircraft that Mark and I flew pulled 4Gs.
Okay, just explain more clearly in the final report. I'm glad that you recalculate the size you upload on Canvas.
Yeah.
You still have like. The calculation was off, I checked last night, but I'm glad you updated it today.
Oh, yeah, the one before was something, it was like a Saturday night, like it was due. And I like went in and like typed it up, but I was like, that's the tomorrow problem for me, because I was busy.
That's for the whole like.
You were like, what is going on with that?
Yeah, we did it.
No, it was, yeah. I think,
Just timing.
Okay,
I mean, there's some calculations. left.
yeah. Atommic strength of aluminum, why do you need to use atomic strength of aluminum there? What is that for?
The spar itself.
Okay. Spar for.
Realistically, we would not want to push it that far either. Just because I'm assuming that in that bending process, there would probably, because that's we would be entering the ductile range of aluminum and some of those higher G stresses. So I'm assuming that some of the plastic may fail under some of those conditions, which was why initially I went with a calculation based on the PLA. But after your guys' feedback last time, I wanted to make the assumption of that the load is transferred into the spars and do that calculation based off the spars, specifically from Mr. Singer's feedback. And I wanted to redo it so it worked out better. But I still would assume that the failure would probably be from the PLA cracking
Yeah, just.
around the spar.
Sure, because I don't see the exact location of your spar, just be careful that the stress, you calculate bending stress. Is really the bottom, because it has been in other group also. The bending stress, maximum bending stress you calculate is really at the top and bottom surface, and if your spar is really not close to the top and bottom surface, like around somewhere in the middle.
That's why we have the assumption of that the 3D print spar that runs along that section goes around and wraps a sleeve tightly around the spar. So we have the assumption that those forces are being transmitted from the surface into the
Location
spar.
on the cross section, where is located on the cross section?
So like, right, I mean, you can see it here better than I'm gonna be able to explain it with my hands. So here's, where the airfoil cross section is here, and it runs through around this, like a little bit above the center line. But because of the
That's what I mean.
EDFs here,
That's what I mean. So it's only about the center line, let's say your center line.
it's a tube, so like it's already set off from the
How
center
much is
axis,
Half an inch.
half an inch. It's a thin wall tube.
That is the cross section, right? That hole is where you.
Yeah, where
located.
you want the string.
That's what I mean, because when you calculate the maximum stress is really the top and bottom surface, but the tube there is somewhere in between, that's what I mean.
I mean, several RC aircraft use tubes that run through the center line, like
Answer my question. You said several aircraft.
what I'm saying is that the assumption is that these 3D printed spars transmit the rigidity of this spar into the outer sections of the wing surface.
You calculate magnet stress here and here. Right? Your tube is here, is close to the neutral surface. What happened to the bending? Neutral surface, bending stress, normal stress caused by bending 0. Your tube is around neutral surface. Maximum stress, maximum are either top and bottom. They are not actually carry the maximum stress. They are closer to the neutral surface where the stress is almost 0.
That may
Right.
be true, but in practice, it
It's true,
certainly
it is
works.
true. It's not maybe true, it is true.
I mean, it certainly works.
No.
And it's
It's,
worked through.
let's talk in this way. Let's forget about the car. You say it certainly works, it doesn't break, but is it too much?
Could it be optimized? I'm sure.
Yeah.
Yeah.
That's what I mean. You can make thinner tube.
But the constraint that we had, and I looked at trying to implement your idea of tubes on the top and bottom, but they wanted to have the thrust tubes set into the wing. It wasn't physically possible to have stringers run or spars running top and bottom. Like
I did it before.
you have, I mean, if you look at the cross section of this particular plane, I mean, it would have
First,
to have
it
run
does
through
not
it.
have to be a tube. So the trainer we used for several semesters, it flew to tree this time, but we repaired many times in previous semester.
With
And
rods, small rods, right?
what?
Was it small rods?
We didn't use rod. So what happened is that somehow one student like had deep dive and then the wing did like this. And then we took the airplane back. We just used some of the wood plate from the Max 3 lab. And we just stick to the bottom. I forgot the top and bottom of surface.
Yeah.
And that was enough.
But that's pretty ghetto.
You guys are engineer.
Yeah.
You know what I mean?
Yeah,
When
I
when I
understand.
ask some structure and then some engineering stuff, don't try to answer it in a way that, oh, some other aircraft or answer my question. I mean,
I mean, I thought there was, and I'm not trying to be argumentative. I mean, I thought a lot of some of the objectives of our design is supposed to be looking at aircraft that work and previous examples of aircraft that work and taking that into
I
consideration.
want to know your analysis of your aircraft.
You'll see it in the final report.
I want to the analysis of your aircraft. Why is necessary to put a tube around the neutral surface? I don't understand. You are calculating stress at the bottom and top surface for bending, the maximum stress at top and bottom, and you put a tube around neutral surface. I don't understand. We can do it better. I mean, yes, it didn't break. But can we make a thinner internal supporting structure to make your aircraft lighter in weight? That's what I mean. So when I ask this question, you can answer purely from solid mechanics, not answer from previous aircraft or something. It really does not need to be a tube. It really does not need to be around the neutral surface. We made it work, just put a plate, stick to the top or bottom surface of the wing, and it worked for several semester. So at this point, I want to say that you guys are like senior engineers. When trying someone like in the future, when you go to Korea, go to graduate school or anything, try to think with engineering mind. You cannot always convince people say that, oh, other airplane did that. That's why we did that. That's not an explanation. I want your calculation. I want your analysis of your design. Otherwise, why I ask you guys to spend one semester design this one? I mean, if you just want to like combine several history data, okay, this aircraft did this one, this aircraft did this one. I just like took all the ideas from the previous aircraft and that this is my design. I don't need you to do this design. Right? So this is the structure part. And page 13. Yes, I just. When you said put it there like flaps, the purpose is to decrease the speed for landing. I cannot understand why you put flaps decrease takeoff speed. The purpose of flaps in takeoff is to decrease speed. Why?
Well, they increase lift they
Yeah,
increase
yeah.
lift so that.
You increase cabin, increase lift coefficient, and you increase lift. But here, from what I read and also explained in presentation, you said decrease the takeoff landing speed. I mean, I can understand the decrease of landing speed. Why decrease the takeoff speed is a purpose of flaps.
Well, it decreases the speed at which it takes off.
I'm
Take a
confused.
rotation speed.
What's your question?
I
So
understand
the flaps itself, it will create drags, it will decrease the speed, yes, of course. But I think the purpose in the takeoff is using flaps is not to decrease speed, it's to increase camber, to increase lift coefficient, to increase lift. That's that's a more reasonable explanation why you use flaps, instead of saying that for takeoff, we want to decrease speed.
Are you saying,
The justification. is
are you
not-
saying that, the reason that, like what we said here, that, we want to decrease our takeoff speed is an improper justification for our flaps? As opposed to-
What do you mean now?
I'm just
You
trying to
said,
understand.
decrease the speed that, the threshold speed that when it take off. Is that-
Sorry, what was that?
Okay, that's what I'm, I think I know what you mean now. Probably you should put it better explanation there, because right now what I feel that, yes, flaps will decrease speed, but that should not be purpose of the flaps during takeoff.
Right.
You can say that flaps can decrease the threshold speed when to lift up, right? Or you can say that flap is for takeoff is to increase camber, to increase lift coefficient, to increase the lift. I can understand that part, but you just put it say decrease takeoff speed, I don't understand. Especially when you put it together with the landing speed. I mean, for when you put it together, decrease takeoff and landing speed, I feel like, okay, flaps generate more drag. Yes, it will decrease takeoff and landing speed, but what is the purpose in the takeoff? That's what I mean.
Okay.
Yeah, that's what I mean. So makes the implementation like not confusing audience. Page 19. Choose a conventional tail configuration to minimize the efficiency disruption from duct fan weighing on. I'm not really convinced that conventional tail's purpose is for that. I mean, there's a lot of reasons we use conventional tail, but I don't think it's like stay away from the wake of the engine, because I mean, if you really want to have some tail to make it stay away from the engine wake or something, you may choose edge tail to push like the work tail like to two sides, or use T-tail to put the horizontal tail like to top. That part I can understand, but when you say that you use conventional because you want to minimize the inefficient disruption from the duct fan, that's the part I can understand.
You're right. Well, we thought about using an H tail.
Yeah.
But then our ducted fans are on either side of the aircraft, so we figured that that would be more in the
Well,
way of.
actually, your duct is like really close to the fuselage. So I would say that if we want for that purpose, I feel like probably H tail or T tail is better.
Maybe we misrepresented how far the cone of the wake behind the ducted fans would be, but we thought that it might still interfere. We also didn't go with the T-tail because we thought that there might be a moment on the aircraft that might be a little
I'm not
larger.
pushing you guys to design the H tail beta, but just purely for the presentation part or explanation part, I don't think a conventional tail function, the advantage of conventional tail is for that part.
I should have written a better explanation.
Well, conventional is efficient, is minimum weight, is easy to attach the fuselage, and structurally is safe, a lot of internal supporting structure. That's the purpose of using conventional tail. But if you want to really say that minimize efficiency disruption from the duct fan, especially your duct fan is very close to the fuselage, I would say choose something else like H tail or T tail. Right?
Yes,
So. $32. It's super cool that you have 3 carbon fiber rods as far as is that necessary, or do you have any calculation persuading me if it's necessary?
We didn't include a calculation here, but we had at least 2 just to, maybe the third one was a little bit redundant. But we had the other 2 to allow, to make sure that the vertical tail section stayed together, to anchor it at 2 points in the front and the back. Otherwise, it could have been minus just the glue that was holding it, it would have been free to
Okay.
rotate.
Okay.
While we're on the subject here, I mean, I feel like you don't even need it to span the whole thing. The glue itself will hold it pretty good, like if you were just worried about like the actual alignment to the to like the fuselage itself, but you were just calling it the shoulder. I
Yeah,
mean, you already had the lap joint essentially, right, to get the shear joint,
yeah,
that already does your alignment, so. I feel like you honestly don't even need the rods, cause like if you're just gonna glue everything together.
well, other than that, there's glue holding this joint together, but there's no lap piece here, it's just a flat 1-layer PLA thick. So there's also glue along these spars to actually hold the pieces together. We can just do 1 mil.
Yeah, I was just, yeah, that's a good point, I was.
Yeah.
wondering, like, you could just do like a little section between just the little pieces there, that way if you're worried about that, yeah.
Yeah, it could have been designed
I'd
better.
say some-
Yeah,
What do
so the main problem of your curve is too heavy, so you just like, for now, just like think all the weights that can reduce the weight.
Yes,
Any place is like this redundancy design. If you can persuade me like it's really necessary based on calculation, then I'm okay. But if it's like, I just feel like I want to do it this way, then
Yeah, we'll go
Yes.
ahead and just use
We're
one
engineers.
carbon fiber spar then, and we'll keep these 2 like PLA spars here, we won't put any rods in them, we'll just use 1 rod right there then.
So, so slide 14, you guys mentioned this Traxxas servo.
Yes.
It's a car servo, do we notice any problems, why would we use car servo for that
Slower,
application?
slower time.
Well, the reason was time constraints, really, was we weren't able to ship one in the time to get it up in the air. But you could also say that since we did have a stabilizer, we didn't need a lot of deflection. So we would be able to get away with having maybe a slower time.
so on this page, I see the work panel with holes, and you said the holes for reducing weight, but my question is, why that panel exists in the first place, what's the purpose?
For stiffness, so we have one on this side and one on the other side, they're not actually as close to the walls as it looks in here. So they provide a little bit of rigidity in that direction.
Okay.
Also, it lets us add these locator holes and mounting, because on this one, we mounted the servo for it.
Okay, okay.
So if I go here, you can have a better view. You can see we mounted our servo on this.
It's also to have a removable nose section, so otherwise if I have to super glue it and then you can't get the batteries in and out of the wire, so it's removable with those 2 screw holes on the back end.
And another thing that when you calculate, 27, I guess, I'm not sure. Okay, I guess it has changed the page number, it was based on the one you submitted. So in your calculation, like the pulse weight ratio, thrust weight ratio, I mean, I think in your further slides, you couple appendix, you show like some pulse weight ratio, and then the power is from the. Okay, now. Your pulse weight ratio calculation or thrust weight ratio calculation may be done. I don't know which page number it is. Okay, so when you calculate this one, did you use the power of the motor directly for calculation, or is there like, because thrust weight ratio, power weight ratio is really the thrust or power of your propulsion system. It's not 100% of your motor power. So I was wondering, when you do the calculation, do you consider like maybe there's some efficiency between the power of the motor and the actual power generated by your propulsion system? Or do you use the same value?
Let me see if I can
explain it, or Justin? you-
This calculation was done at the 75% throttle, and in the initial calculation, there's also a factor for including some like losses that we
Yeah, what
applied
factor
to
did
it,
you use?
75%. And then
That
we
is
did
not-
that on top
That is the 75% of throttle, you use 75%.
for cruise. I'll have to go back and make sure, but I remember whenever we preliminarily did this,
Yes, because.
was
when
a
I read
factor
the
applied to
slides
it.
You upload on Saturday night, I remember you showed the power of your motor, and then you said, okay, I use 75% of throttle, so that is like 75% of that power, and then you use that one for calculation the power to weight ratio. I feel like, yes, that is 75%, but there should be some other efficiency, like, there's like thrust loss from that, right?
Right.
Well, that's.
You
what
need to
this-
put that in the calculation, that's probably why your thrust is not enough, right?
well, so this was based on the initial weight estimate, not the final estimate. That's why on the further along on the slides, there was the true thrust to weight ratio. That's why this was
At
inaccurate.
100% throttle.
Yeah, what I mean that in your fund to make sure that consider the thrust loss.
Yes.
Because without doing anything, you cannot just use the power of motor is a power of propulsion system, it's not same thing. Yeah.
That number is just one of them, right? Just one EDO,
No, that's both of them.
the 2 point, okay.
Page 29.
That's what this is.
Oh, okay, this is 29.
Oh, no, you're right.
Yeah, yeah.
The maximum thrust, I was gonna say.
It's a
thrust-
lot less than.
The thrust to weight ratio is both of them, but
Yeah,
the maximum thrust, yeah, that's just.
No, that's both.
What do you mean by final temperature 90 degree?
I'm sorry,
What is 90 degree?
90 degrees Celsius?
Yeah.
So that's the temperature that's the temperature at thermal equilibrium. So when the energy flowing into the ESC is the same as the energy flowing out, that's the temperature that the ESC will be at when at that condition. Does that,
So
do
it's
you
the
understand?
actual, based on calculation, it's actual temperature of your ESC.
Yes. But this is a,
That's
yes,
actually really dangerous because what's the melting point of PA?
it's about like 200.
150,
It's about
150-ish.
Oh.
Warping is like 70, 60.
Okay,
So,
if you think it's fine.
well, I mean, it's,
Since we're here, you didn't mention this, but you mentioned it all like it's below the melting point of PLA, like I'm not really concerned necessarily about the PLA, I'm concerned about the electronic component itself. And you mentioned this 90 degree C, but you didn't compare that to the actual like max temp of the ESC that you're using.
oh, okay.
So I have no idea what the max temp of the ESC allows, so if you're 90 degree C, I mean, you might be above, below, and obviously you didn't burn it up, so you're below, but. It would have been good to show the number that the ESC is rated to.
Yeah, that's a good point. We did multiple long taxi tests as well before this, and so we've had no issues. So-
The taxi test is nowhere near full power flight or
Well, we've also done full throttle tests as well.
for a
so-
sustained minute and a half.
Yes.
With no airflow.
Yes.
I also have something to add here from kind of the. Like, what it seems like is going on, is this assuming 100% losses? Essentially,
What do
like
you,
essentially, all of the power that is going through the ESC is being dumped into heat. Right,
I'm not exactly sure what
No.
you're saying.
It's assuming that the power necessary to drive the system, propulsion system's going to it, to the motor, and it's getting lost in there, but the remaining power required by the ESC, which is, it's that 67 watts.
okay,
That's that's the heat.
Are you using?
So this is a very like aggressive calculation.
yeah.
This is
that's
like
what I was-
the
what I was
worst
saying.
possible.
Yeah, well,
This is
that's-
a like,
It's good to
upper
do this way
bound.
because you want to be conservative. when you do
yes,
this.
that's
this
what
is extremely conservative.
That's what I was getting at, like that 76 or the 67 watts is the power that is flowing through your ESC, right?
That's the power that's staying in the ESC.
Oh, yeah, but it's
So-
assuming that all of that is being lost to heat.
Yes.
Yes.
Yeah, so
This is very, very aggressive.
very aggressive and very conservative.
Yes.
Which is probably why you're getting 90 degrees
We
Celsius.
do long.
Yes.
So.
Yeah, that's good.
Yes, this is a
Probably-
very,
So I think that temperature is a lot less concerning than it would be
Yes.
otherwise. I would probably just like. Probably worth mentioning though.
yeah, that's fair. I mean, the idea is basically like if our melting point is at 90 degrees Celsius at the most conservative.
Yeah.
Calculation, which is below the melting point of PLA, like we're, in actuality, it's not all going to be lost to heat. We're actually looking pretty solid. So this is not a significant failure mode.
So the convective coefficient that you mentioned at the screw speed,
Yeah.
are you assuming it's laminar, or are you assuming that it's like a turbulent flow?
That's a good question. The figures we obtained, so I'm not sure. We're not looking at like laminar or turbulent. We're just using a simple formula. So, I mean, we're not looking at like heat transfer through a boundary layer or anything. This analysis isn't that advanced. So.
Page 46. So everything else is good. I'm just a little worried about like decrease the filter length by 2 to 3 sections, because you probably need to just do the stability analysis all over again.
Yes,
And you probably need to change the dimension of your tail. And that actually can increase weight.
you say make it larger, or make the tail larger.
If you decrease the filter length, you need to increase the surface area of the tail, right? Which
Well,
will-
it's the,
Or if you are saying it's okay, then you mean that your previous design is not optimized. There's something there.
Correct. Well, I think what happened before in the upfront is that I designed the horizontal tail.
Okay.
And I was not expecting it to be a stabulator at the time. I thought we were going to have a traditional elevator
Okay.
configuration. And then later down the line, it was proposed to do a stabulator. I was overruled. And
So just
so
the
it
same
changed to
dimension.
stabulator, and now you're getting like, because so much area is changing. When you're deflecting the stabulator, and you also have this long moment arm, you get a huge moment out of it, which makes the plane like ridiculously twitchy. And so like the idea is shortening it, would make it less twitchy, but we, like you're saying, we may need to go back and figure out a new surface area for that.
Yeah.
This is
To
a-
make it dialed in.
Again, it's important to remember, this is a very preliminary estimate, so like, we don't have calculations right now.
Oh, yeah, I'm good, I'm good with that, I'm good with that. I just want to mention here, it's not simply just reduce that to the 3 section or any length you want to decrease. It's just like whatever size you want to decrease, the moment arm, you need to consider what's corresponding
Yes.
tail surface area.
Yes,
Yeah,
yes.
you need to do the calculation.
Down to a smaller prediction on SolidWorks, what do you estimate that to be like when you fully put together? Yeah. That's all I have.
And also you guys mentioned like the color is the problem.
yes.
I apologize about all the black ones, because it's cheaper. But I feel like,
It's really interesting to note that the worst thermal effects we had were actually
Solar
related to
radiation.
PLA. or from solar radiation, nothing internal.
Okay.
What?
Okay, so I think one thing is that we can change the color if it's regular PA, we can switch with Storm. Well, for the main design, it doesn't matter, will not stay outside. So I can talk to Storm like change the color with them. And another thing that we probably want to do test flight either early morning or late in the afternoon, not around noon.
Yeah.
So that would be much better because temperature around noon is just crazy. I don't think like, even if we change the other color, probably it's sticking outside. So we may figure out time like early in the morning or late in the afternoon when temperature is much lower. Yeah. And if you want to use regular PA, we I can talk to Dr. Trump change different color. If you want to use regular PA, I can find more.
Yes, that we would appreciate that.
Yeah, so, and also one thing, so, I want to say, I think it's the same thing for the last group, is that, a presentation skill is actually a required skill for our student design class. It's not required for other lecture prep class, like mechanical materials, aerospace structure. We don't require any presentation skill, but it is required, in our student design class, and that's why we had a midterm review. We gave you feedback about presentation purely for the presentation part. And also I gave a lecture about the presentation, and now, I think it's better than the previous, the midterm, but I still feel the whole logic of your presentation is not very clear. It's like the content change here and there. You can check later, like the whole logic of your presentation is not really clear.
What isn't clear about it, out of curiosity?
No, so I think, I don't know, so I have comments that, but I'm not sure if it's like, can you change from, let's start from the first slide. I think this might be from the one you upload on second night, or I don't know if you changed this one. Next one. Next one. So I would consider you can start your presentation from some initial estimation, like what is the taper growth rate, what is the lift drag ratio, what is your target, like the wing loading or something. Instead of give me the details of your wing design, tail design. I mean, at this point you don't have anything yet. Why you show me these details? At the very beginning, I have our requirement. You need to fly 3 laps within 5 minutes. You need to take off within 40 feet. Something like that. Then based on that, like big goal, you have your own estimation based on history data or something like previous aircraft. At that point, yes, we don't have anything yet. We didn't have anything yet. We based on the history data, we said, okay, this is the our goal of maximum speed. With this the goal of takeoff growth rate. This is the goal of our lift drag ratio, wing loading, and everything thrust weight ratio. I would prefer you put that one at the beginning because that's where your design starts. And once you have that initial estimation parameter, then you have the wing design, then you have the propulsion system design, then you have the tail design. But why you show me all the details? I mean, why, like, at the very beginning, I see all the details of wing. Why?
So are you?
I'll add into that just to maybe, hopefully this clarifies what maybe you're about to ask, but basically like having initial estimations on what your airplane parameters should be is something to show first before you start showing us your actual design. And like, it's okay to show the design in the beginning, but to show the initial estimations, to show like what you're actually trying to go for is what you want. You want to show us like, these are like the estimated lift drag, this is the estimated thrust weight, like those are the calcs we want to see before we see your actual design. And then like having these next few slides with the airplane views, you can combine all that into one really concise thing. So after you've addressed your initial concerns or initial estimations, you say, this is what we end up with. There's a quick table of what the thrust to weight is, what the takeoff gross weight is, and then all the views, and then you can show us all on one concise slide, and then you go on to like the actual digging into like the wing design, fuselage design, stuff like that.
Yeah, we want to see a clear logic in your presentation. Start from initial and then choose. I mean, like there should be a big structure for the whole presentation. There should be a like for each topic, like wing design. Why you start from lift ratio or wing loading something, and then this is our target for the wing design, and then this is my design, and this is all the details. And now I have analysis from some like software to prove that okay, from the software analysis, it showed that our wing can generate some of the parameters, some values that satisfy our initial estimation at the beginning, and then okay. Theoretically, it should work. Right, so there should be a structure for the presentation, there should be a structure for each topic. But I didn't see much from your presentation. Yeah,
So you prefer the larger sections of the presentations be more geared toward the requirements of the exercise or the design requirements than the
I
specific
think I
pieces of the,
the requirement of each topic in a logical way.
okay,
Yes, and it's not that I require you guys have to follow my logic. But if you prefer your own way, you need to show me your logic, but I don't think this is a big, good way to show your presentation, like at the beginning, show me I mean, why do I need to know this at the very beginning? I don't even know what's it.
so your concern is it mostly with the very beginning, sorry, or with the
It's
rest
just
of
an
it?
example, this is just one example.
Okay,
But you can
understood.
check all your slides, like from the first one to the last one, I don't see a clear logic in my presentation.
Okay,
This, I just use this one as example, you can move on.
Comment anything, already?
Yeah,
10 minutes over.
Tom, I don't know if we can hear you. Do you have any questions that you put in chat?
I don't know. Can you guys hear me now?
I don't know if it worked. The other problem I had earlier is we couldn't hear him.
Yeah,
Can
I
you join the Zoom
put
and
the
see-
stuff in chat.
And can you give me share privileges again?
We still have time, don't worry, I set this one as 80 minutes per group, so we still have time, and this room is available until, for us, until 2:30. No rush, we still have time.
It's 10 minutes into their.
Yeah, do you want me to tell them that you wanted them to wait until how long? No?
Can Tom talk now?
He said questions are in the chat, but I don't see any in the chat.
Oh,
I
let me,
think
I'll
maybe
repaste.
because I got kicked out.
Yeah,
when
when
you're
you're
Thank you. And can we give me sharing privileges again? I can reshare. Can we hear me?
Test 1, 2.
Oh, there we go.
Oh, here we go. Okay, I'm in. I'm echoey, but I'm in.
His audio is.
Can you guys hear me now?
Okay, great.
Hey.
Yes.
Okay, yeah, excellent. Yeah, I apologize. I'm not sure where the difficulty is coming from, but it could be on Zoom's end, I think. All right, so I know that you guys already have answered a few questions, and I was maybe getting a little distracted. So, your weight, you're 60% over on your weight, right? And presumably you know very well the weight of all your components, right? So that seems like it basically leaves structure, right? So now, if we're talking about just 60% over total weight is all coming from structure, that's a massive miss on the weight of the structure. So where is that coming from?
The PLA mainly, I believe.
Yes, mainly it's the fact that we opted to use regular PLA instead of lightweight PLA.
Is that going to add 5 pounds to, like, what's the weight of just the structure of your airplane?
It's the structure. I think the
Components, it's about like 7.
it's like the weight of the structure is about around 7.
Okay, so was the original design going to be around like 2?
Could you please repeat the question, sir?
Was the original design of the structure going to be around 2 pounds?
I think we were anticipating 5 because
There's about 2 pounds of electronics.
Yeah.
Okay, all right, yeah, that either way, it seems like a big miss, especially because I know when we met a month ago, you had like a double wall fuselage that you've gotten away from, which good job on redesigning that. But it seems like there's weight taken out. So I'm baffled at how the plane got so heavy. But I will say, when Ting was asking last month about, why are you adding flaps to design? You're adding complexity. Well, I mean, this is a pretty good reason for it, right? And if you're going to overshoot by 5 pounds on your weight, the flaps become, a nice thing to have there.
Sure.
Where you're talking about ways to address being overweight, right? You said, okay, well, we can pump more power through the motors, right? We can go from a 4-cell battery to a 5-cell battery, right? But that's gonna increase the weight too, right? So I don't see anywhere on here where you say, if we use the larger battery and pump more power through, where are we actually going to end up on a thrust to weight ratio? And same with everything else, right? If you go to a bigger fan, right, more thrust, but also more weight. Redesign the aircraft. Okay, we can make it shorter, lighter. What do we think we'll be able to achieve when we do those sorts of things, right? So I'd like to see those as, rationale for why these are acceptable fixes.
Right. Well, I mean, preliminarily in SolidWorks, the weight comes down a lot more reasonably, especially with components added. I don't know if you overheard us talking. Maybe that was kind of in the disconnection phase of our conversation, but including the batteries and the ducted fans in the model that I'm working on currently, we are around 7.1 pounds. So it's definitely feasible. So the thing is just nose to the grindstone and finish strong with it.
Okay. Let's see, other stuff on the thermal analysis that you guys did. I appreciate you guys including that, because that was something that we talked about last month. That's very particular to you guys, since you are such a high power aircraft. The thing I'll say there, and well, maybe I'll talk about, because I heard you guys talking about the power being converted to heat is a super conservative number, because it's assuming that essentially all of the power gets converted to heat. Did I hear that right?
Yes, that's correct.
So I'm not a circuits guy by any means, but I'm pretty sure power is amps times volts, right?
Well, yes.
Yes, so correct.
Yes. But,
okay, so that's more like 600, not like 60 watts, right? So I think it's incorrect to state that you're assuming all of your power is converted to heat, right? Because now you're talking about 10% of your power is being converted to heat.
No, so part of that. So we have the current through the ESC and the voltage from the batteries. So we have a total power, most of which goes to the EDFs. The rest of which is into
what is the EDF?
The motors, excuse me.
Oh, the ducted fan thing, right?
Yeah. So we're only considering that heat which remains in the electronic speed controller.
Oh, okay.
Which is
so you are considering that some of the energy or most of the energy is going to kinetic energy of the air being pushed by the fan. Is that correct?
Yes, that's correct.
Okay. Is that, I guess I don't know necessarily how efficient the motors are, but that doesn't sound like radically unreasonable to me. So, okay. So given that, right, if we say, okay, we're going to hit 90 degrees Celsius and that's below the melting point of the PLA, is that the only thing that we're considering when we're looking at the heat transfer analysis?
So the ESCs, if there is a place where we're going to reach the highest temperatures, it's going to be at the ESC.
Okay.
So
and is
focusing our thermal analysis there provides us with a pretty good upper bound for temperatures on the internal side of our aircraft. And if it's basically the hypothesis is if we're if we're successful on the thermal side with this part that is going to experience the most thermal problems, we're going to be successful with the rest of the heat transfer stuff as well. Which
okay, so what I'm getting at then is define success, right? So you're below 90 degrees C. And why is that acceptable? Is the reason that's acceptable because it's below the melting point of the material?
Yes.
Is there any other consideration there about how hot things get?
I'm sorry, what was that?
Are there any other considerations about how hot things get?
Mark was saying earlier about a maximum temp for the ESCs, which we need to look into.
Yeah, but that is true.
Okay, so there's that, right, and then, which is definitely a concern. And then from a structure's point, is there any consideration of temperature there?
PLA does warp at
Yes,
60
warping.
degrees
Yeah.
Celsius, so
Yeah.
there still does need to be some kind of like exhaust for that heat.
I'm sorry, I'm having a little trouble hearing. Could you maybe step closer to the mic?
So PLA warps around 50 to 60 degrees Celsius. So when you mentioned structural problems, that's definitely something that could happen if these numbers were to be the case. So it definitely still needs some kind of exhaust support to, pull some of that air outside of the stagnant.
But
Okay.
again,
So-
these numbers are extremely conservative, so.
Okay. So the other thing, I wouldn't necessarily, say that melting and warping are the only two things to consider with temperature, right? Materials get weaker at higher temperatures, right? So if I'm sure you probably find this for plastic, but I mostly work with aluminums, right? So if you go to a material database and look at aluminum as it gets up to higher temperatures, you'll see the ultimate strength and the yield strength of the aluminum are falling off, right? So 90 degrees C for aluminum was that somewhere in the neighborhood of like 200 degrees Fahrenheit. So aluminum is somewhere around probably 80% of its strength at room temperature. And so that's something that you should be considering for the plastic material as well, right? If you're saying, we're at a high temperature, okay, it's below the melting point, but how strong is it now, right? I mean, if it's turning into essentially bubble gum at that temperature, even though it's not liquid, it may not be sufficient to carry whatever loads are on it. So I would definitely be concerned if you've got plastic getting up to 90 degrees C and there's any kind of load going through that, I would be concerned structurally there.
Well, the good news
And
is
no, go ahead.
the good news is there's not much of a load going through this at all, since the carbon fiber spars transmit aluminum.
Okay, yeah. So and the main structural load in the plane, yeah. And I'm
Yeah,
not
so
sure
the-
exactly where this is in the airplane.
Not the aluminum.
Yeah, it's not extremely
Yeah,
close to
Yeah, this is, the heat flows through the bottom of the fuselage, which is, not structurally important. Or not as important as like the carbon fiber spars, the stringers,
Yeah.
excuse me. So,
Okay. Yeah, just make
Yeah.
sure you're considering that as you're talking about thermal analysis. And then was there anything else I had written down? Oh yeah, so you talked about when you're doing the structural analysis, right? You said we're considering a 7G maneuver. Was that correct?
Yes.
Okay, where does that 7G maneuver come from? Like, how are you saying?
So when I
Yeah,
when
go
I
ahead.
was finding, I'll get closer to the mic too. When I was finding the formula for the max bending moment, like for the wing, it was defined in terms of of load factor.
Yep.
And so I was able to come up with all of the other variables for that equation for like the cruising flight speed conditions. And what I needed to do was kind of set how many G's that it could pull to be able to.
Answer the question, why 7G is not,
Yeah, why
7G?
is it 7G? Like, what is
well-
the plane not capable of pulling more than 7Gs, or are you telling the pilot, hey, don't do more than 7Gs, or like what controls that number?
Okay, so I would say that this is, we definitely do not want to go over 7Gs with the numbers that we have here. And I would tell the pilot to keep it very conservative on turns and really try not to pull more than like 5 or 6 Gs because we already have a factor of safety. How's the pilot gonna know?
If the pilot because remember the pilot's not in the airplane, right? So he doesn't necessarily have a good feel for the G load that is being pulled. So if they're flying straight and level at 80 miles an hour or whatever, and they just yank back on the stick to climb, right? Like what says that's not going to be more than the load you're analyzing for? It feels like that should be something performance based on the airplane.
Right.
Well, Mr. Singer, if I may add, and I told Dr. Ting this as well, the trainer that Mark and I flew had an accelerometer in it. And, you know, the trainer's rated to be around, you know, it can go 40 to 50 miles an hour. That pulled, we pulled 4 Gs with that thing. So 7 Gs for a jet RC aircraft capable of going 80 miles an hour. 7 Gs is, I think 7 Gs.
It feels like I'll grant you that it feels like a lot, right? I mean, it seems like a high number, but there should be some performance measure that says, you know, given the flight conditions I'm in and given the amount of control authority that you have on an elevator, you know, you should be able to obtain whatever the induced load is going to be, right? I mean, that should be a performance characteristic of the airplane. And if it's going to exceed that, then either adjust the analysis or somehow, you know, limit the control authority that you can't exceed that.
Okay.
So basically, so you're saying calculate the load that it can take based on our control authority and those structures rather than the like spars of the aircraft.
No, I mean, what I'm saying is, right, you got to design your wing and analyze your wing based on the loads that can be put into it, right? And if you can deflect that elevator and all of a sudden you're pulling 9 Gs, then you need to analyze for that, or you decide I can't handle 9 Gs, I can only handle 7 Gs, so now I need to figure out how much I can deflect my elevator so that I limit myself to 7 Gs.
Okay. So something for the pilot to kind of have an idea of how much he can actually push the airplane.
Yeah, and I would assume, especially in a RC airplane where you don't have, you know, the pilot in a cockpit and, you know, potentially monitoring like an angle of attack and other sorts of things, right? I don't have a good feel for, you know, how much of the flight envelope an RC pilot is really going to be aware of. So it seems like the better idea to just limit what the airplane can do to what your structure can handle.
All right. We'll definitely look into that for the final report. Thank you, Mr. Singer.
Okay. That's all I had.
Thank you, Tom. We really appreciate it.
Thank you.
Thank you.
Thank you.
I guess, we're like 20 minutes over at this point. But we can let them get in here pretty quickly, but like honestly, from the test flight and from what I've seen, most of the things are pretty good. Like it did seem stable when it was up there and everything. It was just the fact that it was, I mean, you were trading airspeed for altitude and there wasn't enough of either. So I think it really comes down to the weight thing. So it's just sadly a little bit back to the drawing board, but then going through optimizing all of the structures that you can. Hopefully the smaller fuselage and shorter tail while keeping the stability aspects as similar as possible will help with the weight and everything. So I think it's just a crunch to see if you guys can get back in the air. But other than that, I think you guys did a good job.
So, thank you. So overall, great job. I apologize. I was a little crazy when talk about structure part. But I feel that the presentation, everything is like a really great job, and I can see that a lot of work you guys put into the this semester and everything, and I feel like and I'm really happy to see that like in your group, like everybody contribute, because we had a problem with other groups, like only very small numbers didn't contribute and that other people just like, I don't care. But I'm really happy to see that everyone in your group put a lot of work this semester, and I think it is like great. I mean, presentation and like all the design, building, everything, great job. And I think we can make it fun. And if you need anything from me, like ask me, or you need to buy something or anything, just ask me. And like go to the flight get a feedback. I can be there anytime.
It's just like tough to by next Wednesday if on reports do, which this has to be up in the environment.
I can change the I can change. I mean, anything. Talk to me.
Okay.
Yeah, I can.
Because like
Yeah.
if we fly on the same day the reports due, it's very hard to put test flight stuff in the line for.
You can imagine what's gonna happen on Friday. Put your report for. No, I can change the report.
We'll be in the football stadium Friday night, taping up Friday.
Yeah. Yeah. So anything, talk to me.
Yes, ma'am.
Yeah, yeah. Yeah. Thank you.
Thank you.
Thank you, Tom. This